Okay, today we'll discuss about different methods of starting single phase induction motor. Last class, we learned that our single phase induction motor is a non-self starting motor. So we learned that our single phase induction motor is a non-self starting motor, or it is not a self starting motor. Why? Because at starting condition, torque T was 0. Why my torque T was 0? Because we know that T is equal to TF plus TB, but at starting condition, my TB was equal to minus TF. So my torque becomes 0. My torque was 0 at starting condition. So we can say as a torque is 0 starting condition, we can say our single phase induction motor is a non-self starting motor. Now, what are the different methods by which we can self-start our motor? One simple method, which is not actually used or which should not be used, is we can make sure that our TF becomes greater than our TB. How that can be done? If we give any mechanical torque, say for example, if we give external mechanical torque to your motor during starting condition, your TF will become greater than your TB and the motor will start. That is one method. Say for example, take a ceiling fan. Ceiling fan is an example of single phase induction motor. Ceiling fan is an example of single phase induction motor. When the ceiling fan is not operating, say you have switched on your ceiling fan, but it is not rotating or it is not operating or it is not running, what you will do? First, you will take a stick and you will try rotating it. In some case, it will rotate. There, what you are doing, you are making sure that your TF is greater than your TB. That is one method. That is your forward torque becomes greater than your backward torque. So the motor rotates during starting condition. That is one method. So example is just now we discussed that is ceiling fan. We are giving a external mechanical torque to our ceiling fan, so it will rotate. But starting torque equal to 0, to make sure TF greater than TB, we are making use of a stick in a ceiling fan. That is fine. That is not actually encouraged. That method is not actually encouraged. Now, what we can do thereby, our single phase induction motor becomes self-starting. A single phase induction motor becomes self-starting. So first, let us see the applications. We will discuss about the application of single phase induction motor. It is used in ceiling fan, or say it is used in stable fan, and then it is used in most of the home appliances. It is used in most of the home appliances. Okay. Now, what are different methods by which we can make our single phase induction motor self-starting? So that is known as, now the single phase induction motor is made into a split phase motor. So by making a single phase induction motor a split phase motor, it will become self-start or it become self-starting. So in split phase motor, we have two types. One is resistive type, other is capacitive type. One is resistive type, other is capacitance type or capacitive type. So what is use of this resistive split phase motor or capacitive split phase motor? To self-start. This is used to self-start single phase induction motor. IM stands for induction motor. Now first let us discuss about resistive split phase motor. Resistive split phase motor. So what happens in resistive split phase motor? First, let us discuss about the schematic diagram. How it will look like. How this induction motor will look like. That is resistive split phase motor. I will have my main winding. This winding is known as main winding. To my main winding, I will give a power supply. Single phase power supply with voltage V. Then, so say this is my main winding. Then I will have one more winding, which is known as axillary winding. This winding will be called as axillary winding. Okay. Then we have a CFS, where CFS stands for centrifugal switch. So this is my stator side. This is my stator side. That is to my stator winding. That is to both main winding as well as the axillary winding. I give a voltage, that is single phase power supply. So this contributes to my stator. So where is my rotor? My rotor is available here. My rotor is a squirrel cage rotor. What type of rotor is this? Rotor is a squirrel cage rotor. Fine. So in my motor, I have my stator as well as my rotor. Rotor is a squirrel cage rotor, whereas my stator has main winding and axillary winding as well as a centrifugal switch. We will be discussing about the use of all this. Now, what is the other name for my axillary winding? My axillary winding can also be called as starting winding. My axillary winding can also be called as starting winding. My main winding can also be called as running winding. Now my CFS is normally closed. It is actually a switch. It is normally closed. The switch is normally closed. So when it will open and it will disconnect my axillary winding, that we will discuss. Okay. So this is my schematic diagram for my resistive split phase motor. So what we are going to achieve here, we will achieve TF greater than TB. We have to achieve TF greater than TB during starting condition. Thereby, my T is not equal to 0. Thereby, my T is not equal to 0. T stands for torque during starting condition. How that is achieved? It is achieved with the help of the currents. We have a current IM. What is this current IM? It is the main winding current. Current which is flowing through the main winding is known as IM. I have my IA, that is the current which is flowing through my axillary winding. So I have IM and IA. So the current which is flowing through my main winding is known as IM, and the current which is flowing through my axillary winding is known as IA. When you apply a voltage, the current will flow because both main winding and axillary winding, they are close to path. CFS, that is centrifugal switch, is closed now. It is closed now. It is closed now. Okay, fine. Now, if there is a phase difference, as we know, IM and IA, they are AC currents. There will be a phase difference between IA and IM, or angle difference, say phase difference, see angle difference. So this angle difference between IA and IM is called as alpha. It's known as alpha. Difference in angle between IA and IM, that is current flowing through main winding and axillary winding. Fine. Now for Resistive split phase motor, my alpha is more or less equal to 30 degree. For resistive split phase motor, my alpha is more or less equal to 30 degree. So my TF will be greater than TB. My TF will be greater than TB. So my T is not equal to 0 during starting condition. So how this is achieved? How alpha is equal to 30 is achieved? That is a very important question. By making the axillary winding R by X ratio, where R stands for resistance, X stands for reactance, axillary winding R by X ratio is greater than main winding R by X ratio. So if you take a winding, say you take a winding, both are winding. If you take a winding, you will have both resistance as well as your reactance. So we are making sure that R by X ratio is greater than main winding R by X ratio. If that is done, then your axillary current, your axillary winding current will lead main winding current. So how that is achieved? How that is achieved? So make sure that your axillary winding has less number of turns, as well as it is thin. Make sure that your axillary winding is made of thin wire and it has less number of turns. If you do that, then R by X ratio of axillary winding will be greater than your main winding R by X ratio. Very simple. So if this is done, what happens? Your IA will lead your IM. That is, we subtract the angle of IA with the IM, that will be equal to 30 degree. So my alpha is 30, hence my TF will be greater than TB. As my TF greater than TB, at starting condition, the torque is non-zero. So my motor will rotate on its own. My induction motor will rotate on its own during starting condition. So this setup is known as resistive split phase motor. This setup is called resistive split phase motor. Now, what is the use of this centrifugal switch? That is very important. So, during starting condition, CF closed during starting condition. But what happens during running condition? So during running condition, say the motor has reached n naught speed, say nominal speed, some nominal speed, your motor has reached. So during n naught, when the motor reaches n naught speed, CF plus centrifugal switch opens. So a centrifugal switch opens, axillary winding is disconnected. Disconnected from the circuit. You will have only main winding. Now at this condition, when the motor reaches nominal speed, centrifugal switch opens, axillary winding is disconnected, only your main winding will be present. And the rotor will rotate. Now when you switch off, or when you disconnect the power supply, automatically CF will get closed. Once again, when you switch on, CF is closed, so axillary winding is present. The rotor will rotate, it will start rotating, it will reach a nominal speed n naught. Once again, CFS will open, axillary winding is disconnected. So during static condition, axillary winding is present, but during running condition, axillary winding will be absent. That is the use of your centrifugal switch. That is why we have a centrifugal switch. So now we have made our single phase induction motor as a self-starting motor. Now what happens to the, say this is my voltage phasor diagram. Let us go for the phasor diagram for this setup. So say this is my voltage which is applied to the motor. This will be my IA current, that is auxiliary current, and or else we can say I have my voltage. Say this is my IA and this is my IM. So say the angle is 30° between this. So this is my phasor diagram. This part is my phasor. This is my phasor diagram. How about the torque speed characteristics? Now let us discuss about the torque speed characteristics. Characteristics of this setup. So this will be my speed N and this will be my torque T. So initially there is some torque. Initially I do have some torque. Okay. Now when I reach N0 speed, this is axillary winding plus main winding. Here till N0 I will have axillary winding plus N winding plus main winding. But when the motor reaches N0, you will have only main winding. You will have main winding alone. See, you have main winding alone. So what you should do? At N0, it drops. The torque drops. You will have only this. So this dark portion is the actual torque speed characteristics of resistive split phase motor. Okay. See, this is for both. When you have a combination of main winding as well as axillary winding. But during N0, you will have only main winding. This is for main winding alone. So the dark portion is the actual torque speed characteristics of resistive split phase motor. Okay, so this is one type of self-starting your single phase induction motor. Now let us discuss about one more type. So what is that? Capacitive split phase motor. Capacitive split phase motor. In capacitive split phase motor, we have three types. The first type is capacitor run. First type is capacitor start. First type is capacitor start. The second type is two-value capacitor. Two-value capacitor split phase motor. Third type is capacitor run. Third type is known as capacitor run, or it can also be called as permanent capacitor. Permanent capacitor split phase motor. So the first type is capacitor start. Second type is two-value capacitor. Third type is capacitor run, or it can also be called as permanent capacitor. Fine. This is for capacitive split phase motor. Now let us discuss about capacitor start split phase motor. Okay. How does this work? First, let us look into the schematic diagram. How about a schematic diagram? So we will have a axillary winding. Axillary winding can also be called as starting winding. Then we'll have a main winding. Main winding can also be called as a running winding. Okay. So the applied voltage is a single phase voltage 230 volts. Say. Then we will have a centrifugal switch, CFS, which is normally closed. Normally this switch is closed, but at speed N0 it is open. We are talking about the centrifugal switch. Then we have a capacitor. Then we'll have a capacitor C. That is why it is known as capacitor start split phase motor. Right. This is my stator setup, and I have my rotor, which is a squirrel cage rotor. My rotor is a squirrel cage rotor. So this is my rotor. Right. Now how this is going to work? How this is going to work? Now we know the current which is flowing through my main winding is taken as IM. Current which is flowing through my axillary winding is taken as IA. So when the angle difference between IM and IA is alpha, let us say, angle difference between IA and IM is alpha. Now as we have a capacitor in axillary winding circuit and CF is normally closed, it will open only when the motor is running at nominal speed. So here the alpha is equal to, say it is equal to 90 degree. My alpha is equal to 90 degree. As my alpha is equal to 90 degree, the starting torque is good. Good. When the alpha increases, if the alpha increases, that is the angle difference between axillary winding current and main winding current phase angle, if alpha increases, my starting torque also increases. They are directly proportional. So as my alpha is equal to 90 degree, as my alpha is equal to 90 degree, my starting torque is also good. Starting torque is good. So we have achieved TF greater than TB. So my T is not equal to 0 during starting condition. My motor becomes a self-starting motor. As my TF is greater than TB and T is not equal to 0, my motor becomes a self-starting motor because of the axillary winding setup which has capacitor as well. So how this is going to work? Very simple. How this is going to work? So when I give the power supply to both main winding as well as axillary winding, a current IM and IA flows in main winding and axillary winding respectively. I have a capacitor here. As we have a capacitor in, if the circuit has a capacitor, the current will lead the voltage. So IA will be angle angle will be very much greater than my IM, because in main winding we don't have any capacitor. A winding is an inductor on its own. So this IM will lag my voltage, but my IA will lead the voltage V because it has a capacitor in it. So the angle difference between IA and IM becomes equal to 90. So TF becomes greater than TB. T is not equal to 0 during starting condition. So my motor starts, itself start with good starting torque, with good amount of starting torque. Now let us discuss about the capacitor which is available here when this is disconnected. So when the speed becomes, after starting, the speed will become N0. Say it is a nominal speed. When the motor reaches a nominal speed, CFS gets open. As my CFS gets open, the capacitor C as well as the axillary winding is disconnected from the circuit. As well as C and axillary winding, they are disconnected from the circuit. So during running condition, only main winding is present in the circuit. Only main winding is present in the circuit. That is why it is known as running winding, whereas axillary winding can also be called as starting winding. Hope you understand. Let us discuss about the capacitance now. How about the capacitor? The capacitor value is more or less equal to 250 microfarad. In this type of motor, we will be using high capacitor value, which is 250 microfarad, and it is short-lived. The capacitor is short-lived in the circuit because when the motor reaches nominal speed or a good amount of speed, the capacitor disconnected from the circuit, so it is short-lived. The capacitor is short-lived. So we are going to use a electrolytic capacitor. It's made up of, it is a, what type of capacitor is used? Electrolytic capacitor is used. Value is 250 microfarad. Type is electrolytic capacitor. So this is about your capacitor starts with phase motor. We have discussed about the schematic diagram, the functioning as well. Now let us go for phasor diagram. How about the phasor diagram of this particular motor? So I will have my V here, that is the applied voltage. Then I will have my IA and I will have my IM. The angle difference between IA and IM is 90 degree. So this is my phasor diagram. This is alpha equal to 90 degree. Fine. Now let us talk about the torque speed characteristics. Okay. Now let's talk about the torque speed characteristics. So this is my torque and this is my speed. So if both axillary winding and main winding are always present, what will be the torque? See, this will be my torque. It will be high. But what is the actual motor torque for this motor? What is the motor torque? This main alone, main winding alone. So at N0 speed, my axillary winding is disconnected. So this will be, this line drawn in blue will be my actual torque speed characteristics of the capacitor start split phase motor. Capacitor start split phase motor. Right. Now we will discuss about the next type. So our next type is two value capacitor. Two value capacitor split phase motor. Two value capacitor split phase motor. Now let us discuss about the schematic diagram. So how about the schematic diagram? We will have our axillary winding, then we will have our main winding, IM will flow, IA will flow through my axillary winding. I will have my rotor, which is a squirrel cage rotor. Then I will have a capacitor. I will have a capacitor. To this, I will give a power supply, voltage V. Then I will have one more capacitor. This is my centrifugal switch, which is normally closed. When the motor reaches speed N0, it will open. Normally closed, say closed. At N0 speed, opens my centrifugal switch. Say this is my C1 and this is my C2. When two capacitors are connected in series, the capacitance will reduce. When two capacitors are connected in parallel, the capacitance will increase. As if the capacitance increase, then the current will leave it. The current leads the voltage by a huge amount. So here C2 and C1, they are in parallel, so the net capacitance will be very high. So normally C2 and C1, they are connected in parallel with axillary winding. You have axillary winding and main winding. We have a rotor as well. Now what happens? During starting condition, my equivalent capacitance is equal to C1 plus C2. This is for starting condition, during starting condition. So what happens? My IA angle is very much greater than my IM angle. So alpha is greater than 90 degree. As my alpha is greater than 90 degree, the torque, the starting torque is very high. Starting torque is very high as my alpha is greater than 90 degree. So during starting condition, you will have main winding. See, during starting condition, you will have main winding plus axillary winding plus C2 plus C1 in the circuit. Right. What happens during running condition? Say the speed, motor speed has reached N0. You will have your main winding. You will also have the axillary winding. You will have your C2, but you will not have your C1 because C1 is disconnected with the help of your CFS. As my CFS, that is centrifugal switch, opens during running condition when the speed of the motor reaches N0. That is the difference. So what is the advantage of this setup? This setup, what is the advantage? Power factor improves. The motor power factor improves. Motor power factor improves. Starting torque is very high. One more important characteristic, that is C1 is greater than C2. C1 value is very high. C1 value is very high, whereas C2 value is medium. So that is about your two value capacitor split phase motor. Now let us draw the phasor diagram. Phasor diagram. Phasor diagram, what happens? I have my voltage. I have my IM. I have my IA. This is my alpha. It's greater than 90 degree. Alpha is greater than my 90 degree. Okay. Fine. Now, how about torque speed characteristics? How about my right? So this will be my speed and this will be my torque T. Now initially, say this is without, say this is with both main winding, axillary winding C1 plus C2. And this is with main winding plus axillary winding plus C2. You don't have your C1. Right. So this is my N0. At N0, what happens? At N0, I don't have my C1. So the red color, the red curve, the curve drawn in red shows the torque speed characteristics of two value capacitor split phase motor. Right. Okay. Now we have the last type, which is permanent. What is the last type? Permanent capacitor split phase motor, or that can also be called as capacitor run. The last type, permanent capacitor or capacitor and split phase motor. So how that can be obtained? Just from your two value capacitor split phase motor, remove C1 and CFS setup. Remove CFS and C1 setup, you will get your permanent capacitor or capacitor run split phase motor. So you should remove this. So in your permanent capacitor or capacitor run split phase motor, you should remove C1 and CFS setup. So this is removed. So the schematic diagram will be this alone, where you have your axillary winding, you will have your main winding, you have your C2, you don't have any CFS, that is centrifugal switch, in your permanent capacitor split phase motor. So if you remove this, what happens? During starting condition, you will have primary winding, that is, you will have main winding, you will have auxiliary winding as well as C2 during starting condition. What happens during running condition? Even during running condition, main winding, auxiliary winding, and C2 are present. So, what is the use of this? The capacitor presence improves the power factor of the motor. Capacitor presence improves the power factor of the motor because it is available during starting as well as running condition, my capacitor. As well as the starting torque is medium now. What happens now? The starting torque becomes medium. Starting torque becomes medium. The angle difference between IM and IA becomes 90 degree. It's not greater than 90 degree. It is 90 degree for my permanent capacitor split phase motor. It is reliable as well. Why it is reliable? We don't have CFS, so it becomes reliable, and it is low cost when compared to two value capacitor split phase motor. What are the disadvantages of two value capacitor split phase motor? It has CFS, two capacitors, so there are chances that CFS may fail, so it is less reliable. Two value capacitor split phase motor is less reliable, whereas permanent capacitor motor is more reliable because we don't have any CFS. And it is low cost because in two value we have C1 and C2, but in permanent capacitor we have only C2 with medium value capacitance, so it is low cost. But what are the advantages of two value capacitor? It has high starting torque, it has very high starting torque. That is the advantage of my two value, and the power factor is also good for two value when compared with permanent capacitor split phase motor. So these are the different methods. So these are the different methods by which we can start our self-start. More importantly, self-start